Well, it's time to talk about quantum numbers and atomic orbitals, and this is how we start understanding how the electrons are organized within the the atom. And if you remember, one of the things that we've been saying about the electrons is that they are moving around the empty space that is most of the volume of the atom. However, initially with the Bohr model, we were thinking that they were moving in orbits, but then, well, not so much. Those electrons are not actually moving in orbits. If they were moving in orbits, it would mean that we know where they are, because those orbits will be very well defined because they represent a given energy level. However, according to Heisenberg, we cannot know the position of the electron and the velocity at the same time. So to say that we know exactly where the electron is by saying that it is moving around an orbit, then it would be mistaken. So then we don't define orbits anymore. We define regions in space in which we can find that electron. The electron can be moving in any way that it wants to, but it would be moving in a particular region in space that we now define for them, right? And how we define those regions in space, they come from Schrödinger equations, okay? They are very complex mathematical equations that we are not going to see in this class because it goes beyond the purpose of the class. We will focus just on the solutions of those equations because the solutions to those equations are what we call the quantum numbers. Okay? And those quantum numbers will define these regions in space that now we are going to call orbitals. So those orbitals are these regions, and in these regions you will have a high probability of finding significant electron density there. So it's areas in space in which you can find an electron or have a high probability of finding the electron. How many electrons or how they are moving in those regions, it doesn't matter. You are just interested in how many electrons you can put in those regions and how are those regions defined. Okay? So the solutions for these equations, and we usually use the hydrogen atom because it's the simplest one, and it doesn't, there are less things to consider for the hydrogen atom. But the point is that these equations define these regions, and these regions are what we call orbitals. So it's an oversimplification of all the process that they have gone through to define these regions, and we limit our analysis to the 4 quantum numbers. Okay, they are the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin. Okay, just 4. 4 is more than enough. The first 3 are related to the orbital. The last one is related to the electron. Okay, so pretty much the first 3 define the orbital, the last one defines the electron. So this principal quantum number, remember, you were kind of introduced this for the first time when talking about the Bohr model. The principal quantum number defines the energy level, and it can have values from starting at 1 through 2, 2, 3, 4, all the way to infinity. Okay, do you get to infinity? Not really, but you get the point here. So it's integer numbers, whole numbers, starting with 1. So because we relate that to the energy level, well, pretty much what we are saying is that the higher the level of that electron, the farther away from the nucleus it is. Therefore, the principal quantum number is defining how far the electron is from the nucleus. The larger the principal quantum number, the farther away that electron is from the nucleus. Okay? So, to be farther away from the nucleus also implies that that electron has to have more energy. Remember, the nucleus is attracting the electrons. In order to pull those electrons farther away from the nucleus, you need to provide energy. So for that electron to be moving that far from the nucleus means it has absorbed a significant amount of energy. And remember, this principal quantum number defines the energy level, and we were using, I usually use a simplification with a building. These energy levels are represented by the floors in a building. So if they have the same energy level, they are in the same floor, and then they have the same principal quantum number. Now, the angular momentum quantum number it defines the sublevel of energy. And one thing that you may need to get used to is that we call the levels as shells and the sublevels subshells. Okay, but the point is they are a shell of energy, or the first shell, the second shell, they are referred to energy levels or to energy sublevels. Okay. However, for the sublevels, we have a particular name. They have a particular shape and a particular name. Okay, and it depends on the value of the angular momentum quantum number. So if the value of L is 0, then that orbital is called S. L equal 1 is P, D equal 2 is D, L equal 3 is F, L equal 4 is G, and from there you continue in alphabetical order. To this point, if you go to the last element added to the periodic table, we are still not filling the G orbitals. We are just as far as to the F orbital. So technically you only have to worry up to the value of L equals 3. Okay? So now one thing that I want you to consider here is that the values of L are controlled by the value of N. So we're going to discuss this in more detail, but let's say if N equals 2, then L can have all the values from 0 all the way to N minus 2. N minus 1, sorry. So N minus 1 here is equal to 1. So for N equal 2, L can have values of 0 and 1. Okay, so for every time that you add more to the principal quantum number, you are adding another value to L, pretty much. So remember that this is the angular momentum is the level of energy, and I picture that as the rooms, different rooms that you can have in a floor in a building. Now the magnetic quantum number, remember, we have the principal is giving you the energy level, then you have the angular momentum quantum number that is giving you the sublevel of energy. Now the magnetic quantum number is giving you about the orientation, giving information about the orientation of that particular orbital. And now the values of ML goes from minus 1 going through 0 all the way to plus L. Sorry, not minus 1, minus L all the way to plus L. That means if you have L equal 1, then that means that ML can be minus 1, 0, and plus 1. 3 different values for ML. Okay, is the orientation of the orbital. If you count how many different values of ML you have, in this case you have a total of 3 values. That means 3 different orientations of that orbital, of the orbital with L equal 1. Okay? Now to this point we have talked about N, L, and ML. If you have all those 3 values, then you are defining one single orbital. Let me rephrase that. If you have one single value for each one of these quantum numbers, you are defining a single orbital. Okay, so what is the relationship between all these numbers? Because it's going to be really important. In order to understand how the electrons are distributed within the atom, we need to understand what is the relationship between all these numbers, and particularly these 3. So how about we start with N equals 1? Okay, remember L goes from 0 to N minus 1, ml goes from minus L going through 0 all the way to plus L. So therefore, if n equals 1, then L can only have the value of 0. Okay? For L equals 0, the name of that orbital is S, and then we add the number. That number in front of the orbital is specifying that that S orbital belongs to the first energy level or to the first shell. Therefore, if L equals 0, then ML can only have the value of 0, which means we only have one, coming from here, only one orbital in the subshell. Because you only have one subshell within the shell, then you only have one total orbital in the entire energy level. That is for n equal 1. Now, what happens if you go to n equal 2? Right? So remember, L will go from 0 to n minus 1. In this case, now n minus 1 is 1. So L can have values of 0 and 1. Now for L equals 0, that's the s orbital. For L equal 1 is the p orbital. And now we add a 2. So that means that this orbital is different than that one. Okay? They are both s orbitals, but they do not belong to the same energy level. So, and that's important to remember. So now if we go to the values of ML, for L equals 0, ML is still 0, but for L equal 1, now we have ML, let's be explicit here, plus 1, so ML can be minus 1, 0, and plus 1. Now in each subshell, we have one value here from L equals 0, but we have 3 values there for L equal 1. So we have a total, you have 1 in one subshell and 3 in the other subshell, so you have a total of 4 orbitals in the second energy shell. And you see how kind of this is going, or where this is going, right? So because now if L equals 3, you have 3 different values of L. Now here, 3s is the same orbital but belonging to a different energy level. The values of ML stay the same, except that now for L equal 2, now we have 5 different values of the ML quantum number. You have 1 here, 3, 1, 3, 4, plus 5, 9 total orbitals in that energy level. And then if you go to 4, it gets more complicated. Yes, now we have 4 values of L, giving you the corresponding orbitals here, the 4s, 4p, 4d, and 4f. Now you have 7 values for L equal 3 here. You start at minus 3, going through 0 all the way to 3. That gives you 16 orbitals in that 4th level. Okay, so usually this is as far as you go, but for example, if you go to 5, technically you can have a 5G orbital there. It's just that most likely we are not going to use it. Okay, so basically this is as complex a distribution of orbitals as it is going to be for any element that you are going to work with. Okay, you just will change the number in front depending on what energy level you are working. That to say, if you are with n equals 6, you're going to have a 6x, a 6p, 6d, and 6f. There is the possibility for higher orbitals to exist, but as I said before, we are not going to use them. So now the electron spin, and then that electron spin originates another principle that we need to know. So the electron spin, what does that mean? So imagine that you have the electron, right? This is the electron. And what happens with the electron is that the electron is spinning. Okay, it's rotating along its axis. So, and it can do it in one way or the other way. Okay, And depending on what direction this electron is rotating, we assign a spin quantum number, and there are only two values that that spin can take. It could be either +1/2 or -1/2. It doesn't matter where the electron is located in terms of the orbitals. The spin quantum number can only have a value of +1/2 or -1/2. Okay? So now we are ready to represent orbital diagrams, because these orbital diagrams will be sort of the room where you can locate the electrons. And here, it's as simple as to represent it as with a box, right? And inside the box, we're going to represent the electrons with arrows. And if the arrow is pointing up, okay, if the arrow is pointing up, it's going to be +1/2. If the arrow is pointing down, the spin is going to be -1/2. Is there any requirement to put it up and down? Doesn't really matter. Okay, just for convention, usually you put it pointing up, but it doesn't really matter. The point is that whenever you come with the quantum numbers, two electrons cannot have the same quantum numbers, because they will have exactly the same 4 quantum numbers. Okay, they must differ at least in one. And so remember here, for the 1s, for this 1s orbital, n equals 1, L equals 0, and ML equals 0. The three, just by saying 1s, you are already defining those three values. So the fourth number is the spin, and because you have here an arrow pointing up, this spin is going to be +1/2. Now here you have defined the 4 quantum numbers for that electron, for this electron that is here, this arrow that you have there. If you want to put another electron in that box, the first 3 are going to be the same, but if you put the arrow pointing up, then they want to have exactly the same 4 quantum numbers, and that's not allowed. Okay, so you need that arrow pointing down, so that now ms is equal to -1/2, and now you're good to go. That makes that in that particular box you can only put 2 electrons. In any single orbital you can only put 2 electrons. Okay, but more on that when we start electron configurations. So one of the things that you should be able to do is, if you have a set of quantum numbers, can you identify which ones are allowed and which ones are not. So remember, here is the usual format in which you report quantum numbers. So first, principal quantum number, angular momentum, and magnetic, in that order. So the first number would be n, so this column here is n. And unless you see a negative number or 0, you're going to be good with any number that you see there. So you have a 2, a 3, and a 4, and that's perfectly valid. So just by looking at the principal quantum number, you cannot spot anything that is out of the ordinary or that is not allowed. Okay? So now we take a look at the second quantum number, right? This is L. And L must be less than n minus 1. So in this particular one, well, 2 is equal to 2. So this number here is not allowed. You cannot have a value of L that is equal to n. Okay, it's just not allowed. Think in terms of the rules. These are the rules. You cannot have a value of L that is equal or greater than n. So this is not allowed. So we take a look at the second one, and this is 2. So 3 minus 1 is equal to 2. So far this checks. And then in the next one we have 1, and that checks too because it's less than n minus 1. Okay, remember the values of L can be 0 in this particular case if n equals 4, then L can be 0, 1, 2, and 3. So since we have 1 here, then this value checks. Okay, it's allowed. So far B and C, no problem with that. Okay, they are allowed sets of quantum numbers. Now we take a look at ML. So in the first one, we already discarded that because there were already something not allowed. In the second one, if we write this completely now, we have n equals 3, which means L can be 0, 1, or 2. It's 2, so that's good. And if L equals 2, then ML can be -2, -1, 0, +1, and +2. So in this particular case is 0, so this checks. So here, this represents a set of allowed quantum numbers. Now in the next one, we have L equal 1. And for L equal 1, ML is -1, 0, and +1. However, this number here is -2, and -2 is not there. Okay, -2 is not an allowed number for ML given the combination of numbers that you have here. So this is not an allowed set of quantum numbers. So therefore our answer is the set of quantum numbers that is allowed here is 3, 2, and 0. Okay? Now, which set of quantum numbers will identify an electron in a 4p subshell? Okay? So we have 4p, right? This number here, 4, that describes n. So that means n equals 4. And n is the first number, so they are all 4, so they are okay. All of them check. Now, this number here, this letter here, the orbital p, corresponds to L equal 1. Okay, remember, if you have n equal 4, then L can be 0, 1, 2, and 3. However, if we are already giving a name to that orbital, we are already fixing what the value of L is, and for that particular case, for P, the value is 1. So this is not 1, this checks, this is not 1. So we forget about D and A right away because they will not represent an electron in a 4p subshell. Okay? Now for L equal 1, ML can be -1, 0, and +1. So here we have 0, that checks, and here we have -1, okay, we have 0 and -1, those two check. So these two sets of numbers will represent an electron in a 4p subshell. Okay, so the answer is actually E, both B and C. Okay, so those are the allowed, well, sorry, not allowed, but those are sets of quantum numbers that will represent a 4p electron. So now we know about the quantum numbers, we know about the name of the orbitals. That depends on the angular momentum quantum number. Now these orbitals will have a particular shape depending on the value of L. So the easiest to recognize is the s orbital. Okay, the s orbital is for L equals 0 and pretty much is a sphere. Okay, so it's around, there is no, it's symmetrical for all, no matter how you look at. And the thing that we are representing here, because we have 3 different orbitals there, this is the 1s, this is the 2s, and this is the 3s. And what you see here is that Here inside, that's the 1s, which is the same that you have here, and this is the 2s. So the shape of the orbital is the same, it's just that the size of the orbital depends on what the value of n is. Okay, so remember, if the principal quantum number gets larger and larger, then the electron is farther and farther away from the nucleus, and that's what's basically being represented here. You can think that, well, the nucleus here is a really small dot centered in the 1s orbital, and from there it's just getting larger and larger and larger. Okay, so once again, the s orbital is a sphere, so that's the easiest one to recognize. The second easiest to recognize is the p orbital, and for p, L equal 1. If you remember, for L equal 1, we have 3 different values of ml that represents 3 different orientations for the p orbital. And basically the shape of the p orbital, this is what we call, you will see this a lot in books, is dumbbell shaped. That's a p orbital. Okay, so all the 3 different p orbitals that you can have, they are all having the same shape. It's just that the orientation is different. For example, the first one, it's centered along the x-axis. This one is centered along the z-axis, and this one is centered along the y-axis. So that's why you normally will see it as the px, pz, and py orbitals. Okay, do you have to worry too much about that? No, you don't have to worry too much about that. Just remember that there are 3 different p orbitals, and that's enough information for you. Okay, now from there things get a little more complicated. Now if we move into the d orbital, remember it's for L equal 2. There are 5 different values of ml. And if you have 5 different values, it means you have 5 different orientations. So do you have, here is dxy, dxz, dz squared, dyc, and this one. Do you really have to worry about that? No, you don't have to worry about that. Do you have to memorize what the orientation is for each one of those orbitals? No, you don't really have to. The most important piece of information that you need here is that there are 5 different orbitals, and each one, even if you see, if they look like you have 4 regions, they still represent just one single region in space in which you can find that electron. If that region is divided into 4, that's a different story, but that represents one single orbital. This here is one single orbital. Okay, same for the other 5 orbitals. Now, what is the shape if you increase L one more? Okay, now we have the f orbitals, and if you remember, then for ml we have 7 different values. 7 different values, that means 7 different orientations in space, and that gives you, once again, each one of these is one single orbital. Okay, and as such, it doesn't matter how many subregions each one is divided, that one single orbital can only hold 2 electrons. Okay, each one of these. So if you have a total of 7 orbitals here, and each one can hold only 2 electrons, you have a total of 14 electrons that you can have in a set of f orbitals. Okay, so how does the questions in the exam look like? For example, here this is a kind of a lengthy multiple fill in the blanks questions, and we are asking, for example, the principal quantum number. Remember, we have 4, right? N, L, ml, and ms. This is the principal. This is the angular. This is the magnetic. And this is the spin. Okay, if we are going from the principal quantum number, so the principal quantum number has a symbol of n, so this is the first blank, which indicates the distance from the nucleus and the energy of the orbital, so main energy for that matter. The angular momentum quantum number is given the symbol of L, like we are showing here, and it determines we have energy, we have shape, and we have orientation. Okay, so the principal is energy level, the angular is the shape of the orbital, and the magnetic is the orientation. Therefore, in this particular question, L is giving you the shape of the orbital. So that's the answer to the second blank. Now, when n equals 3, the angular momentum, we are still with L. So if n equals 3, then the angular momentum quantum number has a minimum value of and a maximum value of 4. So if n equals 3, then L is going to be 0, 1, and 2. Therefore, the answers here, the minimum value is 0 and the maximum value is 2. So 0 and 2. Remember, this is for n equals 3. So if the question, if we were changing that number there, then you have to adjust your answer. But L will always have the minimum value of 0. Now, this has to do a little more with the Rydberg equation, but you don't really have to do a calculation here, because one of the things that you have to remember is that if we were looking at the hydrogen atom, right, we have here the ground level, and then we have here the, forget about this one. These are the excited states. Okay, and if we apply quantum numbers to this is 1, 2, 3, 4, 5, and let's add the 6. Okay. Now here we are going with transitions. Which transition represents emission of a photon with the greatest energy? Okay. So how about we picture all of the, how about we change color here? So the first A here is telling you you are going from 2 to 1. So you're starting here and you are going there. Then you are going from 3 to 1, so 3 is here, and you are going to 1. Then you are going from 6 to 3. Then you are going from 1 to 4, so you are starting here, and you are going to 4. And then you are going from 2 to 5. You are starting here at 2, and you are going to 5. Okay? Now you are looking for emission. So if you are going for emission of light of a photon, then you have to go from a high energy level to a low energy level. How low, how high, doesn't really matter. The thing is you are going from a higher level to a lower level, and that will correspond with the emission of a photon. If you are going the other way around, if you are going from a lower level to a higher energy level, then you have to absorb a photon. And so therefore this and this one, this is absorption. Okay, therefore if we are not looking for absorption, we are looking for emission. So these two we discard them. Okay, and now we are looking for the greatest energy. The photon with the greatest energy will correspond to the greatest difference in energy between levels. So the excited states are kind of closer to each other. So if you were to rank these according to energy, you start with 6 to 3 will have lower energy than 2 to 1, and 2 to 1 we have lower energy than 3 to 1. So when it comes, and these are all emission. So if you're looking at which one of these will have the greatest energy, well, it's the one with the greatest energy difference. That would be 3 to 1. So the answer here is B, because that transition will correspond to, number one, emission of a photon, and number two, the greatest energy on a photon compared to the other two. Okay? Now, in this one, we are also looking for allowed sets of quantum numbers. Okay? And in this case, we have two sets that are allowed. So on the first one, we have n equal 1. And if n equals 1, then L can only be 0. And if L is equal to 0, then ML can only be 0. That means 1, well, always check, 0 checks, and 0 checks. So this is one of them. The next one, we have n equals 3. For n equals 3, well, even without this, you know that there is something wrong there. L can only be 0, 1, and 2. This is 4, it doesn't check. So we can forget about that one right away. On the third one, we have n equals 3, which means L equals 0, 1, and 2. And for L equal 2, because this one checks here, then ML can be -2, -1, 0, +1, and +2. And this is a -2, so this one checks. So this is the other allowed set. But just for the fun of it, we have this one, n equals 1, L equals 0, and ML is supposed to be 0, but you have a value of 1 there. That is not allowed. So this is not a valid set of quantum numbers. Okay? So this is all about the quantum numbers. The quantum numbers will define the orbital, and the fourth one, the spin, will define the electron within that orbital. And probably the main thing to remember here is that there are allowed sets. The principal quantum number kind of control the value of the other quantum numbers that you have there, the angular momentum and the magnetic momentum quantum number. Okay? So that's it for now. And next step is electron configurations.